So we'll continue to finish up this, the last part of this theory session, and then we'll move ahead to the next chapter, which we will focus on giving you examples of, we'll talk about two systems. One is the 2G system, the other is a 3G system in details, all right? So I guess last time we were talking about this wake receiver. So remember, by spreading and despreading, we can enjoy an interference discount factor of 1/64. If I chop a symbol into 64 pieces, then every time I come across a certain interference power, I don't need to worry about the total interference power. The only effective interference power that would affect me would be just 1/64 times of the actual interference power, right? So that's the so-called interference suppression capability. So last time we have illustrated pretty much how spectrum interference suppression can help to eliminate or suppress two types of interference in a cellular network. One is the multi-user interference. Remember, in a base station operated using CDMA. So all the users transmission, they share the same time, same frequency, right? So they're not separated by time, not separated by frequency. So how do we separate the signal? Is making use of this selective reconstruction of the signal from a particular user. So, and that basically is one instance of the so-called interference suppression, in particularly suppressing the interference from multi-user. And then we also talk about interference suppression in the second type of interference, that is the inter-symbol interference, right? Because we have multiple resolvable paths. So it will be interfered by the echoes of the previously transmitted symbols. And that will cause the irreducible error flow. And then we also illustrate by spreading and despreading, according to one of these despreading timing, we will be able to suppress the interference and reduce the error flow. So that was the wake receiver architecture. Okay. So last time I haven't talked about then how do you know where. So for successful despreading, right? We need to know two things. One is the despreading code, and last time I explained in all systems, in all CDMA systems, there will be explicit signaling arrangement to tell the receiver what would be the spreading code used by the transmitter. Okay, so the knowledge of the spreading code is usually done through explicit signaling. But what about the despreading timing? Now the despreading timing is something tricky because even the base station do not know about the despreading timing, right? It is you. And the despreading timing depends on your current location as well, right? So in fact, for keeping track of the spreading timing, so this is the typical arrangement. The base station and the transmitter, they will transmit a certain beacon signal. We call this pilot channel. So let's say this is the pilot channel. And the first, this shaded part denotes the first chip of this pilot channel. So this is the pilot channel, which is transmitted periodically. So this is the pilot. Now the pilot does not contain any useful data. Okay, the pilot is just like a known reference symbols. So let's assume the reference symbol is all 1. And then chopped into 64 pieces. So we have a pilot spreading sequence. So that would be pretty much the pattern of the pilots. So base station transmitter, in addition to all the other traffic channel, the base station will also send one reference signal called pilot channel. The pilot channel, the first chip of the pilot channel will be synchronized with the first chip of the other traffic channel. For example, if this is the traffic channel to a certain user, so this is S1T, C1T. The first chip of the data channel transmitted to user 1 will be aligned, synchronized with the first chip of the pilot channel. Okay, the data channel contains useful data, but the pilot channel doesn't have any data. Okay, it's just a fixed data pattern. Let's say all 1. Okay. So now, if I'm the mobile, how do I know what's the despreading timing? Let's say in this example, there are two resolvable paths from the transmitter to the receiver. So let's say this is the first path. So in the first path, let's say this is the pilot channel. And then this is the data channel. And then this is a certain delay, okay, at tau 1, which the base station and the receiver doesn't know. And then this is the second path. And in the second path, let's say this is the timing. This is a pilot channel. So the black color represents the pilot channel. And then the blue color represents the data channel. Okay, so this is a second delay position. Okay, now you are the mobile. You are the mobile. So you know how to, you know the spreading. So the mobile, in order to, okay, the mobile, in order to despread the data channel, the blue part, it has to know two things, right? One is the despreading sequence, okay, which, as I said, is informed. You are notified of the despreading sequence, C1T, by an explicit signaling channel. So you know C1T would be the sequence you use to despread the data channel. But what you don't know is the despreading timing. What you don't know is what is tau 1, what is tau 2, right? So in this case, you will try to do a exhaustive search. So what you do is you first should try to despread the pilot channel, okay? So you know the spreading sequence for the pilot channel as well. So this is defined in the standard, will be the same in all base stations, okay? So how do you despread the pilot channel? You know the despreading sequence, CPT, but you don't know the despreading timing. So, but fortunately, because the pilot channel is periodic, right? So you only have finitely many possible despreading timing. So let's try to do an exhaustive search. So what do I mean? Now this is a mobile station, receiver. So it has a local copy of the despreading sequence. Okay, so let's say this is a despreading sequence corresponding to the pilot channel. What it does not know is where should be the despreading timing. So it will try to do exhaustive search in the following way. So it tries to despread the pilot channel at this timing position. Now in this example, if you try to despread at this local timing position, you don't see any match for both the first path and second path, right? So after this is like despreading the pilot channel with the wrong time. As we talked about last time, if you despread with the wrong time, after despreading, these broken pieces appears as broken pieces, right? Remains as broken pieces. So when you have this timing, you get, so let's say this is the timing. So at this timing, you get very low response because you don't have a match, right? So the next timing you try should be this timing. Again, this timing doesn't match, so you keep on having low response until you keep on trying, until when your local timing becomes this timing. You find that your local despreading timing match the first path timing. So in this case, the response will be large. You reconstruct the pilot reference, right? So, and then you will find a response like this. This is a tau 1. You keep on trying until you are at the second timing position, let's say here. And in this case, when you despread at this second timing position, you match the second timing for the second path. And then where you get a large response as well. So you will have a profile like this, right? So when you do this exhaustive search. So when you have a profile like this, it gives you two information. The first is what should be the correct despreading timing. So at this peak location, that corresponding timing position would be the despreading timing. So this will be the timing for the first path. This will be the timing for the second path. And if this is what you find, you know that there are only two despreading timing. Okay? The peak, the level, give you the corresponding channel gain. Because when you despread the first timing, the first path is affected by alpha 1, right? So the response will be proportional to the gain of the alpha 1. If you despread with respect to the second path timing, then second path is actually affected by alpha 2. So when you match the timing of the second path, the response peak will be proportional to alpha 2. Is that okay? So it gives you several information. Number one, by counting the number of peaks, you know how many possible or how many resolvable paths you can see. That's number one. Number two, you know what's the corresponding despreading timing for each of these paths. Okay? And number three, by looking at the peak, you know which path is stronger, which path is weaker. Okay? So you notice that in this block diagram, there is a guy called searcher. So the searcher is trying to do this exhaustive search for the timing. Okay? So by the output of the searcher will be the possible despreading timing. Okay? So that's why you see that the output of the searcher is trying to drive the despreading timing of individual despreaders. So in my example, if I only have two resolvable paths, the searcher will output tau 1 and tau 2 as two possible despreading timing to configure two despreader. Okay? So as I said last time, if you have 10 paths, if you have 10 paths, you will find 10 peaks here. Okay? Let's say you have 5 paths for easier references. Okay? You have 5 paths, then these are the 5 possible despreading timing. Okay? Last time I said that, okay, overall complexity of this wake receiver will be given by the number of fingers, right? So if I have 5 paths, I will need 5 fingers, 5 despreader to fully despread this 5 paths, right? So, and therefore, the worst case complexity is proportional to the number of resolvable paths, right? So this is nice because this is a linear scaling instead of exponential scaling, as we talked about some lectures ago. However, still this is expensive. If we are talking about 100 paths, then do I need 100 despreader? So the question I would like to explore is, if I only have, let's say, 2 despreader, if I only have 2 despreader, but this time the searcher find there are 5 possible despreading timing. Okay? Or let's say I only have 1 despreading finger. I can only afford 1 despreader hardware. Okay? 1 physical despreader. But now there are 5 possible despreading timing as found out by the searcher. So what would you do? What would be the output? So how would you configure? You are the searcher now. So what would be your decision to ask the only despreader where should the despreader to despread? Which timing should the despreader trying to despread? If you only have 1 despreader, and now you are the searcher, you find that there are 5 possible despreading timing. This is tau 3, tau 4, and tau 5. So now you only have 1 despreader. So what would you do? Using common sense, you should ask the despreader to despread at this 3rd timing, right? Why? Because this guy have the strongest channel, right? Strongest channel means the observation, the W3, after despreading, this W3 will be most reliable, right? The W3 will contain mostly the useful part, a little bit of noise, right? Okay? So now the question to you is, let me erase this. Remember I said that the error probability curve, this is SNR in dB. We say that if you do spread spectrum, if you do not have spread spectrum, let's say just BPSK on a frequency selective fading channel. So this is the error curve you have, right? You have a very slowly decreasing error probability curve in this noise limited region, and you have irreducible error flow in the interference limited region, right? So that was the 2-star travel we talked about. And now, if you have 1 despreader only in the wake receiver, now, okay, if you have 5 despreader, so you can despread over this 5 despreading timing. So you can have W1 up to W5, right? And then you do diversity combining, you do MLC combining on this 5 diversity measurement. Then let's say your error probability curve becomes something like this. So this will be diversity combining with W1, W2, up to W5. Is that okay? So that would be something you would obtain with 5 despreading fingers in your hardware, right? But let's say this is too complicated. In the hardware design, I only have 1 physical despreader. Okay? So, and as I said, the searcher in this case would assign the strongest path to despread, right? So if this is the case, what would be my error probability curve with this only despreader? Will I have this slope or will I have this slope if I only have one despreader? Now, this is amazingly very similar to the case study we talked about in the Wi-Fi chipset design, right? At that time, we say that if you only have one single RF and ADC chain, would you still be able to exploit two-order diversity with two antennas, right? And at that time, I said that this is yes, right? By using selection combining, you can push the selection process from baseband all the way to the antenna front end, right? And by doing that, you can actually enjoy this two-order diversity with only one RF and ADC chain. This is similar. Now I only have one despreader, okay? I only have one despreader. The searcher assigning this despreader to despreader at the third timing, what is it called? This is actually selection combining, right? Because the searcher, after selecting one out of these 5 possible despreading timing, the searcher is trying to select the strongest path, right? Strongest path means the most reliable observation, right? So this is inherently, you are exploiting selection diversity. Is that okay? So therefore, the error probability curve with one single despreading finger would be something like this. So this is with one finger. In this example, despreading on W3. You notice that the slope is the same. So you get the same diversity order as if you have five despreading finger. But you suffer from a penalty. The penalty is, since you're doing selection combining here, so the signal-to-noise ratio is not the same as having 5 fingers. So you lose out 5 times of energy. So you have a horizontal shift. Okay? But the diversity benefit is the same. Is that okay? Whereas in this case, the reduction of the error flow, this is determined by the spreading factor. It's the inherent interference suppression capability. If you are chopping a symbol into 64 pieces, you will get this 1/64 increase in the saturated SINR. So therefore, your error flow will be reduced. Is that okay? So what I have illustrated is, even with single despreading finger, even if you have a constant number of despreading finger, you can still exploit full diversity through selecting the strongest path to despread at the searcher. Okay? So this is once again to illustrate the advantage of using selection combining. Although selection combining is not the optimal way of combining diversity observations, it still maintains the same order of diversity. Okay? And with selection combining, you can save the hardware, expensive hardware, by doing the selection not at the baseband, but at the searcher. Okay? By doing the selection at the searcher, you can do full diversity with only one despreading finger. So, okay, that's the same idea as the Wi-Fi chipset case study. Okay, so in practice, we usually have in the CDMA mobile, we usually have 4 despreading fingers. Okay, and then with 4 despreading finger, you can also use that to support any number of despreading path, any number of resolvable path. Okay, if the number of path is more than the number of fingers you have, you just select the strongest from this available candidate. By selecting the strongest, you are already exploiting the full diversity order. Okay? Any questions? Now, so that is basically the principle of wake receiver. So it's very flexible and very low complexity. All right, so now I guess we talked about this random CDMA already. So random CDMA is the number of users, the capacity limit is interference limited. So how many users you can accommodate is determined by how much interference you can tolerate. Because each time when you introduce a new user, it will increase the interference level a little bit by delta, right? And then so you keep on increasing more users, inviting more users into the network, the total interference level will keep on rising until you cannot tolerate any additional interference. So that will be your capacity limit. And we worked out the equation already. So at the end, the number of users you can support is simply given by the spreading factor divided by the required SINR. Okay, so if you talk about capacity comparison, now remember there are 2 types of CDMA. The first type is what we call deterministic CDMA. You try to design the spreading sequence so that they are completely orthogonal. In this case, if your spreading factor is 64, you can at most accommodate 64 users because you have at most only 64 orthogonal vectors on a 64-dimensional space, right? So, and in that case, the deterministic CDMA has a capacity of 64 if your spreading factor is 64. Now, if you try to compare the capacity with FDMA, TDMA, you'll find that they have the same capacity under the same constraint, okay? So there's nothing more from this arrangement. Now, if you do random CDMA, on the other hand, if you do random CDMA, your capacity is limited by the interference level. Now, if you do the math, we'll find out that the number of users that can be supported using random CDMA is even less than deterministic CDMA, okay? So, and that's also understood because now with random CDMA, each time you invite a user, there will be some increase in the multi-user interference level. Whereas in deterministic CDMA, each time you invite a user, there won't be any increase in interference because the interference will be 0, okay? So that's the, so right now, so that will be the situation. And then you may start to question, in this case, what's the benefit of using CDMA? The capacity of deterministic CDMA at best is the same as TDMA, FDMA. In the random CDMA situation, it's even worse than that, right? So what is the benefit? So it seems like there is no benefit in using CDMA, right? And if there is no benefit, then what for, right? So now of course, one reason for using CDMA is for 3G system, the transmission bandwidth is much larger. So if you do not use CDMA, you have to live with this long channel memory. You have a severe intersymbol interference. So one motivation of using CDMA is helps you to overcome this severe multipath effect, okay? And so therefore, it can help to push the error floor lower and lower. That's one motivation, important motivation. But in terms of capacity, seems like there is not much benefit at this point, right? Now we'll keep this in mind for this question, okay? Now let's look at the extension. Now so far, we come a long way. We talk about point-to-point, and then in this previous part, we talk about multi-user, but in the context of a single base station. So now let's further extend the horizon to look at multi-cell. So in a typical based cellular network, we have more than one single base station. We have multiple base stations. So let's formally talk about the concept of cellular architecture. Let's see if I have the slide. I don't have that slide. So let me do some preamble. I guess in the early lectures, I asked you guys a question, right? So if you look at the history of wireless communication, we start to have this mobile phone services actually in 1920s, around 1920s. That's the New York City. So at that time, there were some deployment of wireless telephone, wireless communication service. But that is for some proprietary system. It's for some special services like police or fireman officer, okay? It's only restricted to a limited set of users. But in terms of the technology, in terms of hardware, in terms of communication infrastructure, that has been around in 1920s. But if you look at the mobile phone services, the first generation system, for example, AMPS, is only around 1980s, where we have the world's first mobile phone services, okay? So this is almost 60 years. So what is the missing gap? Why it took people 60 years to have the world's first mobile phone services? So what is the missing piece? What do you think? As I said, right, in 1920s, you already have the hardware, transmitter, receiver design, radio tower, everything is kind of deployable at 1920s. So why it took people 60 years before we can have this kind of mobile phone services, first generation system? There must be something big missing. Otherwise, it won't take that long, right? And that missing piece is very challenging. that people cannot find solutions for many years. So what's the problem? The key issue is capacity scaling. As I said, the 1920 system is only for a limited set of users, like police, officer, firemen. It's about a few thousand people, okay? But for mobile phone services, it's targeted for the entire population. It's talking about millions of users. From a few thousand users, you need to scale to millions of users, okay? So how do you do it? How do you do it? Now, the brute force way to do it is you need more spectrum, right? You need more spectrum. So the brute force way to do it is, if I need to scale the capacity by 10 times, the brute force way, the easy way or naive way is whatever you call it, you just increase the spectrum by 10 times, right? Then you can accommodate 10 times more users. However, now you are talking about not just increasing the capacity by 10 times. You are talking about increasing the capacity by tens of thousands of times, right? So that is something that cannot be done. Obviously, your available spectrum cannot be increased by tens of thousands of times, right? Because as I said, good spectrum are very limited, right? Even today, you won't be able to easily expand the bandwidth by 10 times, not to mention thousands, tens of thousands of times. So to bridge this capacity gap by just naively increasing the spectrum is just not the solution, because there won't be that amount of radio spectrum available, right? Because we are talking about a huge number of scaling. So that is the missing piece. At the end, what's the solution? So how would people figure out the solution? The solution is very nice. It's called cellular architecture. This cellular architecture is actually, there was a patent invented by Bell Labs in the 50s, 50s or 60s, okay? But of course, fortunately, this patent has expired today. And you will find that even today we are talking about 5G, the basic architecture is still based on cellular architecture. So with cellular architecture, what is the advantage? If the y-axis is capacity, x-axis is the number of base stations. The key motivation for adopting cellular architecture. By the way, cellular architecture means we try to split the coverage area. Now, before cellular architecture, in the 1920 system, the architecture is very simple. You want to minimize the cost, the infrastructure cost, to provide good coverage. So at the end, the solution was you install a few radio towers on some very tall mountains with blasting very large power, just like today's TV tower. Just to give an example, in Hong Kong, the TV radio broadcasting tower is only around less than 10 transmitters to provide the entire coverage for Hong Kong, okay, for TV and radio. But if you look at the number of base stations in the typical operators in Hong Kong, we are talking about, even the small operators, is about 5,000 to 10,000 number of base stations, okay? So it's a huge difference. So the idea, so before in the 1920s, they just installed a few high power radio transmitters on some tall mountains, so as to maximize the coverage or minimize the number of transmitters needed for coverage. So coverage was the key issue at that time, okay? But then when you want to scale to the population capacity of the population order, then it's not the coverage that matters, it's the capacity becoming the bottleneck. So the cellular architecture is like, instead of installing very big radio tower, the overall coverage now is served by many, many small base stations, okay, as we get used to today. So that is called cellular architecture. Now the motivation of cellular architecture is you expect with this cellular architecture, the capacity can scale with the number of base stations. You expect a line like this, okay? So that means I can increase the capacity by installing more base stations in my network. Now the key thing here, very important key thing here, along this curve, when we scale up the capacity, the bandwidth is the same. So that means the reason we can increase more capacity, the reason we can accommodate more users, is not because we have more bandwidth. The bandwidth is the same along this curve. So what's the reason we can scale up the capacity? The reason we can scale up the capacity is due to one thing: resource reuse. For example, if we do FDMA, I have a 15 megahertz of spectrum, right? Using the toy example we talked about previously. Using FDMA, we can partition into, let's say, 600 channels, right? And then we're going to assign one channel to one user. But if I do it this way, I can only at most accommodate 600 users, right? But 600 users is very far away from the population. So the way I can increase the capacity is by, okay, for channel 1, I'm not going to just assign to one user. I'm going to assign to multiple users, okay? So that's called resource reuse. So therefore, the cost of one channel would now be shared by many, many users in the system. But how is it possible that we can reuse the resource? How is it possible that we can reuse the resource? Because if I'm using channel 1, assigning channel 1 to this user, and assigning channel 1 to another user, there will be interference, right? So there will be interference. So, and because of that, we should not be able to reuse the channel, right? But why we can reuse a channel? The fundamental reason we can reuse a channel is because we have path loss. Path loss means what? The receive power is inversely proportional to the distance separation to a certain alpha. So at that time, when we talk about path loss, I asked you guys a question: is path loss your friend or your enemy, right? Now, in terms of coverage, of course, path loss is your enemy, because with heavy path loss, your coverage will shrink, right? But in terms of capacity, exactly because of this reason, because we have path loss, that enables us to reuse the resource. And because of resource reuse, we can scale up the capacity by installing more base stations. So fundamental reason why we have today's cellular network, very affordable cellular network, is because of path loss. So path loss is your very important friend. Without path loss, I can say even today, we won't have affordable mobile phone services, okay? So, and cellular architecture is a very clever architecture that exploit or make use of this path loss effect and turn this enemy into something helpful. Okay, so now I'm going to talk about what exactly, or what's the detailed mechanism of this resource reuse in a multi-cell system. Now to understand the resource reuse issue, so let's consider two extremes, okay? So the first extreme is complete reuse. So let's say I partition 15 megahertz of spectrum into 600 channels, right, using this toy example. And let's say I have a field, this is my coverage area. And let's say I'm very aggressive. I try to assign each base station with the same set of frequency channel, 1 to 600, 1 to 600, right? Now, if that's the case, that's called complete reuse. Now, if I do this, what is the capacity? The capacity in my toy example would be each base station have 600 channels, right? And then if n is the number of base stations, my total capacity would be like this, right? So that would be a line with a slope of 600, a very steep line. So that would be very good, right? If I'm the operator, I would be very happy because the capacity will translate to revenue, right? So if I start with 600 channels, but I scale it like this, complete reuse, ask every base station to reuse the same set of 600 channels, then my capacity just scale up like this. Very good, right? So what's the problem with this kind of aggressive scaling? Now, if you're the user, you will be pretty unhappy, right? Because in this case, you may have a base station 1 transmitting to user 1 on channel 1. And then you will have a adjacent base station talking to its own mobile, also on the same frequency. Now, when this happens, what will be the problem? This transmission will have leakage, right, into the adjacent users. The other adjacent base station transmission will also have leakage, right? So this will be the crosstalk interference. Is that okay? Now, if you still cannot imagine, just imagine Now in this classroom, suddenly there is another professor coming into the classroom. And I'm talking to this half of the class. The other professor is talking to the other half of the class simultaneously. So how would you feel? You will feel very chaotic, right? Because when I'm talking here, this side will hear my voice as well as the other professor's crosstalk. Likewise, the right-hand side of the class, listening to the second professor's messages, will hear my voice as the crosstalk. So you won't be able to hear anything, right? So heavy interference. So if the user in this extreme scenario, complete reuse scenario, you will be very unhappy. You have poor quality of service, right? So now you see that how aggressive we use the resource is a trade-off consideration between capacity, that's the operator's performance metric, and quality of service, that's the user quality of service, the user performance metric. So in this extreme, I'm biasing towards the operator's concern. I'm ignoring the user's concern, right? So that's not a very good operating mode. Is that okay? Now, let's say I swing to the other extreme. Let's say I'm very concerned, I'm biased towards the user quality of service, ignoring the operator's concern. Then what would I do? In this case, suppose I have a 20 base station here in my coverage. So if I'm very concerned about user quality of service, then what should I do? Well, I shouldn't allow any interference, right? So I would divide my 600 channels into 20 sets, right? So each one gets 30. So for the first base station, I will assign channel 1 to channel 30, second base station, channel 31 to channel 60, so on and so forth, right? In this way, no two base stations will be using the same channel, right? So that means throughout the entire network, there won't be any interference. The system is only noise limited. So in this case, the quality of service will be extremely good, right? Because there's zero interference. No multi-user interference at all, right? But in terms of capacity, what would be the problem? The total number of users I can support is still 600. I didn't scale up the capacity, right? So from the operator's perspective, operator will be very unhappy. From the user's perspective, user will be very happy, right? So good quality, but poor system capacity. So obviously, these are two ends of the spectrum. We shouldn't operate our network in either of these ends because that is not a trade-off, right? So completely biased to the user or completely biased to the operator is not the right way. So we want to operate somewhere in between. So what do we mean? So we introduced a parameter called reuse factor. So this is how it works. Let's look at this example. Now if my reuse factor is called 7, so what I would do is I will first divide my 600 channels into 7 sets, okay? So, and assign the first base station to transmit on the first set of channels. And then the next immediate neighbors transmit on the second set, third set, fourth, fifth, sixth, seventh, okay? After that, I have used up all my channels, right? So in the 8th base station, I need to start reusing the channel. But I'm trying to assign the reuse pattern carefully so that, for example, this base station 1 and this base station 1, we call this co-channel base station. Co-channel base station. Or co-channel cells. These co-channel cells means there are 2 base stations using the same set of resource. Okay? Now, so I try to arrange this assignment carefully so that these co-channel base stations are maximally separated. Okay? Now, how would that help? Well, we mentioned that in this first extreme, if every base station we use the same channel, we have interference like this, right? So the quality of service is very poor. And now with this reuse factor of 7 example, I put the co-channel cells, I separate the co-channel cells by some distance. So how would that help? So in terms of this picture, this is like I move the co-channel base station to here. So in this case, it is using the same channel. And we still have crosstalk. How would this situation be different from the initial one? This distance, if this is d, this distance is much larger than d. How would that help? This is where path loss come into the picture. Remember, path loss is what? The receive power will if my path loss exponent is 4, let's say, so that means if I double my distance separation, my receive power will be reduced by 16 times, right? So in this way, that means my signal cannot propagate too far, right? If I double my distance, the receive power will be reduced by 16 times. That's a lot, right? So this is the distance traveled by the interfering signal, by the crosstalk, right? Compared to the first scenario, the crosstalk has to travel a long distance. So by the time that this crosstalk reaches the receiver, the signal, the interference power will be substantially attenuated due to path loss, right? Compared to the good signal. The good signal just needs to travel a distance of d, small d. The bad signal needs to travel a distance of capital D, which is much longer, right? And by path loss phenomena, the bad signal, the interference signal, will be much weaker than the good signal. Is that okay? So by separating the co-channel base station sufficiently far, the SINR received by every user will be increased. Is that okay? The larger this co-channel base station separation is, the larger the SINR would be. This is like my analogy in the classroom, right? Let's say indeed there is a second professor coming into the classroom simultaneously to talk to the two halves of the class. But let's say now the two professors are sufficiently separated. So let's say we extend the space to a very by 100 meters, okay? So in this case, although we are talking simultaneously, the crosstalk on this side of the students who are listening to me, you will still be affected by the crosstalk of the other professors by 100 meters away, right? So now the crosstalk will be much weaker compared to my voice. So your SIR would be much higher than before, right? Likewise to the other side of the class. Is that okay? So that's why we say that path loss is your friend. Because the fact that this interference power will be reduced is due to path loss. If there were no path loss in this world, then it wouldn't make a difference between this setup and the original setup. And in this case, there won't be any opportunity for resource reuse. Is that okay? So that's why path loss is a very important friend in allowing you to reuse the channel to scale up the capacity. Okay? Now, so this is an example of a reuse factor of 7. Now, this is an example of a reuse factor of 4. So now, reuse factor of 4, that means my 600 channels is divided into 4 sets. So each set get 125. So I use the channel 1 to channel 125 for this base station. The adjacent base station, I use the second set, third set, fourth set, etc. Now, by doing this, again, using careful assignment, this shaded cell are the co-channel base station. So with a reuse factor of 4 compared to the reuse factor of 7, we see that the co-channel base station will be closer to each other, right? On the other hand, when a reuse factor of 12, so I divide the 600 channels into 12 sets, then in this case, the co-channel base station are further separated compared to this baseline case. Is that okay? So from this, you can see that by controlling the reuse factor, we can adjust the trade-off between resource reuse and the quality of service. Okay? Now, if I use a very small reuse factor, my capacity formula would be 600 channels divided by 4, right? So this is the number of channels per base station times the number of base station. Since this denominator, which is the reuse factor, is smaller, so my capacity curve will be scaling up faster with a steeper slope compared to the case of the reuse factor of 7, right? So this is a reuse factor of 4. If I have a reuse factor of 7, my capacity will be 600 divided by 7 times n. So obviously, this line will have a flatter slope compared to this line. Is that okay? So from an operator's perspective, capacity scaling perspective, I would rather have this, right? But the trade-off is if I have a reuse factor of 4 like this, my co-channel base station will be closer. So therefore, the interference, the power of this crosstalk will be higher. So the user signal to interference ratio, the quality of service will suffer. Okay? On the other hand, if I use a reuse factor of 12, in this case, these co-channel base stations are very far apart. So this crosstalk power will be very small. So user quality will be very, very good. But with a reuse factor of 12, I will have this capacity. This capacity will scale up very slowly. Is that okay? So therefore, this reuse factor will be a parameter that we can use to adjust the trade-off between operators' concern and users' concern. Now, if I set the reuse factor to be 1, that reduces to this original case, complete reuse, right? Reusing very aggressively. If I set the reuse factor to be equal to the number of base stations, then this is like the second extreme, no reuse. Is that okay? So somewhere in between would be a trade-off between these two concerns. So in other words, let me erase this. If we look at this, capacity versus number of base stations, we expect a curve like this. Okay? Now, if we have a reuse factor of 7, it will be a curve like this. If we have a reuse factor of 4, it will be a curve like this. Okay? And don't forget, we are talking about a few thousands or tens of thousands of base stations in a typical operator. Okay? In Hong Kong, a typical operator has 5,000 to 10,000 base stations. So that is a huge difference. Okay? Now, when you see a steeper curve, that means you are reusing more aggressively. Okay? For a slower curve, that means you're reusing more conservatively. So what determines, so usually the typical setup is like operators would like to use the smallest possible reuse factor subject to a certain required quality of service. So the quality of service experienced by the user would be like a constraint. So operator would like to put the co-channel cells closer and closer until the quality of service experienced by the user will just meet the requirement. Okay? So as I said, right, so the signal to interference ratio experienced by user is actually proportional to the reuse factor square. Now, don't worry about how we derive this. So this is some result. But on the other hand, the capacity is like inversely proportional to the reuse factor. Okay, so basically that gives you a trade-off. If you want to have a more aggressive scaling curve, you would like to use a smaller reuse factor. But with a smaller reuse factor, the SIR experienced by user would be small. Okay, so at the end, it's a trade-off. Just to give you an idea, for first generation system, for example, Eesm, Advanced Mobile Phone Systems, which is the 1G system in the US, is based on FDMA. Now the transmission is actually FM. FM is a nonlinear modulation. So if you study communication before in undergraduate, you should remember FM is a nonlinear modulation. So it has something called capture effect. So to make sure that the quality of, so the voice quality, so FM transmission would require very high SIR in order for you to be able to receive a good quality of the modulation. So, and therefore the SIR requirement is pretty high, 18 dB. So 18 dB after some calculation, the smallest reuse factor will be 7. So for first generation system, you have to maintain a reuse pattern like this in order to meet the quality of service per user. So therefore, the capacity for M system is number of channels per base station. So total number of channels you have, in my example, 600, right? But it can be other numbers. Divided by 7 times the number of base stations. That would be the capacity. And this number of channels divided by reuse factor is the slope. Is the slope of this curve. Okay? Now in the 2G system, in the US, they have something called digital amps. Okay? It's a digital version similar to, it's based on TDMA, similar to GSM based on TDMA. Now, so the transmission is now upgraded from analog FM to digital modulation. With digital modulation, you can tolerate higher interference because you have error correction coding, etc. So you can tolerate more interference, meaning that you can afford to put the co-channel cells closer to each other. So at that time, the reuse factor, the required SIR for the physical layer to operate properly is just 13 dB. In other words, 2G system, digital amps, can tolerate 5 more dB of interference. This translates to a reuse factor of 4. So for 2G system, they can afford to have this reuse pattern. They can afford to put the co-channel cell closer to each other. Okay? And the overall benefit for this is the capacity will scale faster because the slope is higher. Okay? So that's one factor. That's one factor that the digital amps can give you more capacity. Now the second factor is because of digital transmission. In digital amps, your speech, your voice is digitalized, like the MP3, and then going through some speech compression. Your speech is compressed. So one channel, one FM channel, which is I think 30 kilohertz bandwidth. In amps, each user requires 30 kilohertz bandwidth for FM transmission. For digital amps, for the same 30 kilohertz bandwidth, they can support 3 users. So effectively, the number of users or number of channels per base station is increased by 3 times as well. So these two things together contribute a massive increase in the capacity of 2G systems. Okay? And that's why in 2G, the voice capacity is no longer an issue. So we have more than sufficient number of channels for supporting voice users, starting from 2G. Okay? Now, for CDMA, so let's not worry about the detailed calculation, but for CDMA, as I said, what would be the reuse factor you can imagine for CDMA? If all the base stations operate using CDMA, what would be the reuse factor? The reuse factor for CDMA system is actually 1. Why? Remember how CDMA works? In CDMA, within a base station, within one base station, transmission, the broken pieces transmitted by each user, they share the same time, same frequency. So even for users, we call this intra-cell users. Within intra-cell users, we don't need to worry about interference, right? Because you have this magical interference suppression. So within a base station, you don't need to worry about interference among intra-cell users. What about inter-cell users? The users from different base stations? If you can handle intra-cell user interference, you may as well handle inter-cell interference user as well. So because of that, for CDMA system, the reuse factor is 1. You can have a complete reuse. Every base station transmit can be operated on the same carrier. Okay? Because of this, as I said, right, if you compare the capacity versus number of base stations, for random CDMA, the number of channels, if you just consider one base station, is even less than that from TDMA or FDMA, right? But the real benefit of CDMA is when you consider a huge number of, when you scale up the capacity in a multi-cell system. CDMA system allow complete reuse. But for TDMA, FDMA system, you have to have a certain reuse factor, okay? And therefore, the slope increase faster than the others. So that's the real benefit of CDMA system in a multi-cell setup. Is that okay? So that basically concludes the entire part 1, entire theory. Okay, so far we come a long way. We talk about how do we represent information and source, and then how do we communicate information from one point to other point over a very simple channel, additive white Gaussian noise channel. And then we talk about a more realistic channel, fading channels. And then we talk about multi-user communication in a single base station. And then finally, we extend that to multiple base stations. Okay? So now, with this, this will enable us to have a common language so that when we talk about practical systems, we'll have the language to explain why things are designed in a certain way. All right? So now with this, let's look at the next chapter, which is practical systems. Now, in view of time, I will just focus on 2 systems, 2G and 3G, as 2 separate examples, and talk about the detailed system design. Now, let's look at the 2G system. In the 2G system, we will pick the world's first CDMA system, IS-95, as the target systems. So IS-95 is actually invented by Qualcomm. It's actually the first application of mass spectrum technology into cellular system. Okay, and because of this investment in technology, Qualcomm's own a lot of fundamental patents related to CDMA technologies. And later on, when people upgrade to 3G, 3G is entirely based on CDMA. So Qualcomm owns a lot of fundamental patents, and it earns huge amount of money from licensing these fundamental patents in CDMA systems. So I will talk about this later. So let's focus on this IS-95. So this is the system architecture for the IS-95 or 2G CDMA systems. We have a base station. We have a number of base stations connected to a base station controller. A typical base station controller will be used to connect a few hundreds of base stations. And then a number of base station controller will be connected to a mobile switching center. So this is a boundary. The connection interface between base station controller and the mobile switching center is called the A interface. So A interface is the boundary between, this part is called core network, and then this part is called radio access network. Okay? So in this chapter, we will focus primarily on the radio access network. And in the next chapter, we will focus on the core network. So the entire end-to-end picture for a cellular network can be pretty complicated. Okay? So hopefully, we'll have the time to go through this end-to-end flow so that you have a holistic understanding of the entire cellular network. Okay? Now, so sometimes if you have problems in one base station, you will only have outage for a few hundreds of users locally. So that's not quite a big issue. But if you have an outage on the base station controller, that means hundreds of base stations will be out of service. And in that case, it will be a huge impact. So in terms of the equipment provisioning, usually in the operator, base station is just by itself using some alarm monitoring to monitor for any potential issues. But for base station controller, they usually have hot standby arrangement. So base station controller, later on I will give you a picture. So base station controller is like a huge computer. So by hot standby, that means they have two sets of computer and two identical set of software running in parallel, and they stay synchronized. So if there is any problem on one side, the other side can pick up immediately. Okay? So it's hot standby arrangement. This is to reduce the downtime because the impact for having problems at the base station controller and also the mobile switching center will be huge. Now, so this is a 2G system. So it's not a standalone network, right? So 2G system, the cellular network, has to connect to the largest public voice network. So what's the largest public voice network? It's the PSTN, the mobile phone, the public switch telephone network. Okay. Now the connection actually have two concerns. So in a 2G network, so there is a gateway mobile switching center. It's going to interface with PSTN. Now when we say interface, there are two paths. The first one, the data path, is based on what we call PCM 64 kilobit per second interface. So this is based on, remember in the beginning we talked about how to convert analog signal to digital signal. So we have sampling and quantization. So this is called pulse code modulation. So for the mobile network to deliver a voice packet to the PSTN, it has to deliver using the known format. This is the standard format. If you are confused about this PCM, this is like dot wave format. Okay? So when you deliver a speech packet to the PSTN or the PSTN deliver a voice packet to the mobile network, the data path, they have to exchange dot wave format, the voice packet in dot wave format. Okay? Otherwise, the other side won't be able to understand or decode accordingly. That's the data path arrangement. The other interface standard is the control path. So this is the control path. The control path is based on something called SS7, signaling system number 7. This is like, think about that as the command languages. So this control path is not involved in delivering the user payload. Your speech will not go through the signaling path. But this signaling path is used for call setup or call release. So when you set up a call, you dial the number. So this number will give you, give the network an idea how far I should set up the trunk. Okay? Set up the data path. So this involve some signaling languages. So the standard interface for the PSTN for the control is SS7. So at that time, if you have a 2G network, any 2G network that wants to interface to the PSTN, the data path, you need to speak the dot wave language. The control path, you need to speak this SS7 language. Okay? So IS95 as one of the 2G standard 2G system also needs to interface to this largest public voice network using these two interfaces. Okay? Now, of course, in this chapter, we will focus on the radio access network, that is from base station controller below. But in the next chapter, when we talk about the core network, we will talk about something related to SS7. Okay? There is also two guys here, home location register and visiting location registers. These two guys, again, we'll talk about this in the next chapter because these are the core network services. But these guys are just distributed database. So this database is to keep track of the instantaneous location of a user. Okay? So sometimes when the mobile network receives an incoming call, how would the network know where to find you? That is coming from this distributed database. So again, this is called location update services. These location update services will be the topic in the next chapter as well. So we'll talk about this detail in the next chapter. So now let's focus on this radio access interface. Now in IS95, in order to understand IS95 operation, which is a CDMA system, in fact, I would say in order to understand the operation of any CDMA system, you need to ask for the three major important components. First one is called call processing. Call processing. Call processing means how do you set up a connection. Now in 2G, this is for voice. Voice is based on what we call circuit switch mode of connection. So when you call somebody, before the circuit path is established, there is a lot of background signaling going on so that the network will know how to set up the data path between the caller and the called party. So this is called call processing. That's number one component. In 2G, this is called call processing for circuit switch setup. In 3G, in 3G, the reason you can be online 24 hours is because there is a new mode of connection. It's called packet switch connection. So when we talk about 3G, we also will talk about the packet switch call processing. So now let's focus on circuit switch call processing. That's number one component. Number two component for CDMA system is power control. As I said, power control is very important, not just to save the battery power, but to make sure that the random CDMA system can operate. Because if you remember, the 2G, the random CDMA system, when we calculate the capacity, I make a very important assumption. No matter whether you are close to me or far away from me, the received signal power is the same, right? So that everyone, when you enter into the system, you contribute equally the same amount of delta, right? So how do you maintain this condition? This is maintained through careful power control. So that's the second component we have to explain. The third component, in order to understand this CDMA system, is the handover process. The reason that we need to worry about handover is exactly because of cellular architecture. With cellular architecture, the coverage of a base station is very limited. So if I start a call in a certain base station, but then I will keep on moving. So as long as I cross the cell boundary, my call will be interrupted, right? So the handover arrangement is to make sure that despite the mobile crossing the cell boundary, this kind of mobility will be transparent to the voice user. The voice user shouldn't be aware of this cell boundary crossing. The voice user shouldn't also need to do anything about this. Okay, so therefore, there will be a lot of background handover signaling in between your conversation to make sure that this mobility will be transparent to the user, and that is called handover. So we will talk about these three essential elements. Okay. So about synchronization, this is actually what we just talked about. So every base station have a pilot channel. So this is a broken pieces of every pilot channel. So for successful despreader, the receiver needs to know the despreading timing. So how do you know the despreading timing? The searcher will have to do exhaustive search, trying to brute force despread the pilot channel at all possible despreading timing position, right? in order to identify what are the possible despreading timing position. So this is done through the base station transmitting a reference channel called pilot channel. Okay. So, and that's the so-called time synchronization. Now let's focus on the call processing. Okay. Now to explain the call process, before we explain the call processing, let me explain the arrangement of the logical channels. Now in IS-95 systems, so let's say if you have 15 megahertz of spectrum and after that you partition into 600 channels, in my toy example. Now in reality, not all these 600 channels can be used to carry user traffic. Okay? Some of this channel needs to be sacrificed, with what we call overhead channels, in order for supporting the call processing mechanism. Okay? So same for IS-95. So in a downlink, for the downlink, the spreading factor is 64. And they are using deterministic CDMA. That means the orthogonal sequence are chosen to be zero cross correlation in the downlink direction. Because downlink direction can guarantee synchronous despreading, right? So that is not an issue. So therefore, with a spreading factor of 64, you have at most 64 orthogonal channels. So they label the channel using this wash code 0 to wash code 63. This is called wash code. These are the design of the orthogonal codes, okay? Named after this guy, Wash. But then not all these 64 channels are used to carry traffic, as I said. So they are divided into two types of channel. The first type is called common channels, or overhead channels. So from its name, these are provisioned by the base station, which you cannot use that to charge users. So they are overhead. So these channels cannot generate revenue. So there are a few downlink, so in the downlink direction, there are a few common channels. The first one is called pilot channels. Okay, so this is spread using the first wash code W0. So this W0 up to W63, 64 wash codes are all defined in the standard. Each label have a specific patterns. Okay. So this is the first overhead channels, and we have explained the reason for using this for transmitting this channel is to have a reference, timing reference for mobiles to search the possible despreading timing. So this carry no information. There is no information from this channel. So this channel is just like a beacon. The next channel is called sync channel. This is spread on W32. So these are all defined in the standard. So every sync channel on every base station will be spread using this particular key. Okay. Now the sync channel contains some useful information. For example, it contains something called system ID, network ID. With this system ID, network ID, you will know which operator you are listening to. Okay, so every base station will broadcast through the sync channel the system ID and network ID. From that, you will know which operator. It also will broadcast the GPS time. So I will explain this later. So this sync channel will contain some broadcasts, some useful information. Okay. And then the third common channel is called paging channel. So the standard allows the base station to set up at most 7 paging channels. So this is W1 to W7. So this is configurable. If the traffic is light, you can just set up this base station with 1 single paging channel. If the traffic is heavy, you can set up 7 paging channels. Okay. Now this paging channel is like a broadcast channel. It will broadcast a lot of important system parameters. So you can imagine it's like this. If you are like a mobile station, so you random walk into some area. Let's say there are no walls here, okay, between the classroom. You are just random walking in a certain area, blindfolded, okay. So maybe somebody dropped you in somewhere and you just wake up, okay. You have no idea what's going on. You don't even have the same timing as the system, okay. The very first thing you need to do is you need to listen to this sync channel broadcast. So every classroom have some regular broadcasts. So in the sync channel broadcast, it will tell you the time, it will tell you the ID. By listening to this ID, you know which operator you are talking to and what will be the system time. Okay? And then you also need to listen to the paging channel. The paging channel will be another broadcast channel. Again, in every room there is another broadcast. This broadcast will tell you a lot of protocol-specific parameters. So you need to know these parameters before you can participate in this interaction with the system. Okay, so this will be the downlink overhead channels. So obviously these channels will exist by the base station. When you set up the base station, you need to keep on transmitting these overhead channels, and you cannot charge users for using these channels. So they are overhead channels. Okay, they cannot translate into revenue. This is one type of channels. The second type of channel is called dedicated channel or dedicated traffic channel. From its name, it's dedicated. That means it's set up for a particular user. It's only set up when you need it. Okay, so the other watch codes not used can be used for supporting a traffic channel. Okay, so you can see that we start with 64 channels. We have to use 1, 2, and then 7. So 9 channels is used up. So the remaining 64 minus 9 would be the available traffic channels. Okay, these traffic channels, they are assigned to a user, so you need to pay for this. So you can charge revenue for user using this traffic channel. Is that okay? So you need to pay for this. So that's why in 2G, circuit switch mode of connection, you need to pay for the airtime. If you talk to your friend for 2 minutes, you need to pay for 2 minutes of airtime. That's how they charge you. Is that okay? Now, in the uplink, again, spreading factor is 64. You chop a symbol into 64 pieces. But in the uplink, as I said, because you cannot have synchronous despreading, you can only operate random CDMA. Now with random CDMA, you have plenty of codes available. You have thousands of codes, right? So even random code will be able to achieve small cross-correlation. So the code is not an issue. So in the uplink direction, so this is in the uplink. This is in the downlink. In the uplink direction, what we have is, again, we have overhead channels as well. The only overhead channels is called access channel. This is spread using a certain access code defined in the standard as well. Okay, so this is the only channel available for the mobile to talk to the base station. Okay, when you are in a so-called idle state. So this is common. Again, you don't charge a user for using the access channel. So this is a common channel or overhead channels. The second type of channel, dedicated channel, is also called dedicated traffic channel. And this is in the uplink. And then this is dedicated for a user. So the connection is full duplex in 2G. That is, when you set up a voice call for a user, you will set up a downlink dedicated traffic channel as well as an uplink dedicated traffic channel. It appears in pair because the voice surface is full duplex. You can transmit and you can receive at the same time. Again, you have to pay for this. Is that okay? So the channel is now organized in the following way. Okay? Downlink is using deterministic CDMA. You can support like 64 orthogonal channels. But uplink is based on random CDMA, which is interference limited. The number of channels you can support is limited by how much interference you can tolerate, right? And at the end, give you some typical figures. This is 64, but in the uplink it's only 15 to 16. Okay? So therefore, in IS-95, the bottleneck is actually uplink, because the number of voice users, each voice user requires one downlink traffic channel and one uplink traffic channel. You have 64 minus 9, this amount of downlink traffic channel, but you only have around 15 to 16 uplink traffic channel. So at the end, the bottleneck is the uplink. So there were a lot of research at that time trying to improve the uplink capacity. So, and because this is the bottleneck, capacity bottleneck. Okay? Now, after understanding this organization of the physical channel into this kind of logical channels, let's try to understand the call processing. So the first order, so the way to understand call processing is usually implemented in the form of a protocol stack. The protocol stack is a piece of software, right, running some logic. So the way to design or understand or comprehend a protocol stack is usually a state machine, because any software is like a state machine, right? So a state machine is like this circle represents different state, and the arrows edge between the circles represent state transition events. So when something happens, the state will move from this state to the next state, etc. Okay? So the label behind each of these arrows would give you the condition for the state transition to happen. So that is called a state transition machine, right? So any software, when you do implementation of a certain protocol, you need to first understand the state transition machine of the protocol before you can write codes to implement the logic behind the protocol stack, okay? So now this is the top level. We call it tier 0. So in this tier 0, we have, for example, you power up your mobile. You just wake up, okay? You have no idea what's going on. And then the first thing you need to do is to go through some initialization state. By initialization state, that means you need to adjust your local timing to the system timing. Now, for instance, CDMA system in IS-95, if you look at this architecture, this is a synchronous system. Synchronous system means all the entities in the network runs on the same clock. So this base station and the base station controller would have the same notion of t equal to 0. So they run on the same clock. Mobile switching center also have the same notion of t equal to 0 compared to all the other entities. Okay? So how do they do that? Now, these are the fixed line entities. So they are connected by cables of optical fibers. So they can have their own synchronization system. And what about base stations? So in those days, it's not like today. Today, every mobile have a GPS, right? But at that time, GPS receiver is not that low cost. So every base station will have a GPS. So they buy GPS, in GPS, they have a GPS clock. So base station from this GPS receiver will be able to synchronize their local clock across these base stations. 5,000 or 10,000 base station, each of that has a GPS, and through the GPS clock, they achieve the timing synchronization among this base station and all the other entities. Okay? But the mobile phone is also supposed to have the same time reference as the rest of the network, right? But this is something you may not have control, because now if you just switch on the mobile, it's just like you just wake up from nowhere. Your local clock will for sure be different from the system clock. Okay? So the first thing you need to do is, by so-called initialization state, is you try to find some ways to initialize your local timing to the system timing. So that's what the initialization state is trying to do. Okay? I will explain this mechanism in a minute. Now, after you achieve the synchronization state, then the next step is the idle state. The idle state is actually, you are not idle. So by idle state, that means you don't have any traffic channel set up for you, but you have to keep on monitoring the paging channel for potential broadcast, potential update of the parameters, as well as potential call requests, incoming call requests. If there is anybody calling your mobile, how would you know? The incoming call request will be coming from the paging channel. Okay? So you have to keep on monitoring for any potential events. So if nothing happened, you don't make an outgoing call yourself, you don't press the send button. And if there is no incoming call for you, nothing happens, you can stay in the idle state forever. Okay? So this is like most of the mobile right now. So if you want to make a call, you're always ready to make a call. Okay? If there's somebody call your mobile will be able to ring anytime. Okay? But if you do not do anything about this, you will just stay in the idle state for a very long time. Now, if anything happens, let's say you press the send button to make an outgoing call, then you will go through some intermediate state called system access state. So the system access state there will be some procedure for the mobile to talk to the base station about what exactly do you want, right? And after successful access, then you go into the traffic conversation state, in this state, you will have a traffic channel in downlink and uplink set up for you, and you need to start paying for the airtime. Okay? So maybe you engage in a conversation with your friend. After you finish the conversation, you hang up, then you will go back to the initialization state and stay in the idle state. So that will be the top level state transition. Okay? Now, let's zoom into the initialization state. In the initialization state, what do? You power up mobile, right? Power up yourself. You just wake up from nowhere. You don't know what's going on. The first thing you need to do is something called system determination state. Now, the background of this is IS-95, the 2G system in the US. In the US, the way they introduce 2G is they want to have a backward compatible system, backward compatible to their 1G M system. Okay? So therefore, all the 2G system, IS-95 for CDMA or IS-54 for digital M's, both are US standards. They require the mobile to support dual mode. Okay? They require the mobile to support the analog 1G system as well. So the first step is the mobile, your 2G mobile, your CDMA mobile has to determine whether you should log on to the 2G network or log on to the first G network. Okay? So let's say you log on to the 2G network. Then you proceed to pilot channel acquisition. In this pilot channel acquisition, as I talked about just now, okay, the mobile will try to do exhaustive search to find the possible despreading timing for the pilot channel. Okay? Now, of course, the pilot channel has no information. So why would the mobile want to despread the pilot channel? The only motivation is if you find that this despreading timing can despread the pilot channel, the same despreading timing can despread all the other channels as well, because they are transmit in synchronous position. Okay? So the motivation for despreading the pilot channel, the so-called pilot channel acquisition, is to find out what are the possible despreading timing. That is what we talk about in the searcher. Okay? Now, after you successfully despread the pilot channel, you know what are the possible despreading timing. Okay? Then what you would like to do is you keep the same despreading timing, but you change the despreading code from W0 to W32 because you want to listen to the same channel. Okay? The despreading timing for the same channel will be the same as the despreading timing for the pilot channel. Okay? So what you need to do is you just need to switch the despreading code to W32. In this case, you will be able to despread the messages in the same channel, right? So what are the messages in the same channel? As I said, it contains system ID, network ID. From these two ID, you will be able to know which operator this base station is, this roam is broadcasting, okay? If this is your operator, then you will be able to display the operator logo. Maybe China Mobile, maybe PCCW, I don't know, right? Also, the same channel also contains a GPS time. Remember, this GPS time is what the base station network used to synchronize itself, right? To achieve the same timing, system timing. Now, you are the mobile station. When you wake up, your local clock will definitely be different from the system clock, right? But you listen to this broadcast. This broadcast will tell you what is the current time. From this GPS time, you can adjust your local clock. So then, therefore, you go through this timing change substate. This timing change is you adjust your local clock so that you have the same t equal to 0 notion as the system t equal to 0. Okay? So after this fourth step, after the timing change substate, your local clock will be synchronized with the network clock. Okay? So then the entire IS-95 network will be in a synchronous mode. Is that okay? So that will be the initialization state. Any questions? So after you finish the initialization state, you will have the ability to despread any of this downlink channel, including the traffic channel, because you know the despreading timing. Okay? And because of that, you will have to, from time to time, listen to the same channel and also paging channel. Now, what is the inside the paging channel? Now, paging channel will deliver different numbers of parameters. For example, system parameter message. Each of these parameters are some important parameters of some call processing protocol. So you need to know these parameters before you can participate in the call setup. We'll explain some of this later. So you have some system parameter message, you have some access parameter message. So access parameter message will be broadcast to all users in idle state, and it will contain all the essential parameters that you need in order to go through this access state. Okay? and also have some neighbor list message. Neighbor list message will contain something relevant to soft handover. So we'll talk about this in the handover when we talk about handover. CDMA channel list is also about handover. Now, so all the messages A, B, C, D are common message broadcast to all users, except the page message. The page message is dedicated to a particular mobile. The page message will contain incoming call requests. So if somebody call your number, then the network will, through the paging channel of a particular base station, it will send a page message. This page message will contain your ID, will contain your SIM card ID. Okay? Then you listen to this page message, and you only respond, take action if this page message is for you. Okay? So all the other message, A, B, C, D, are common message broadcast to all users. But the page message is dedicated to a particular mobile. Okay? You just ignore the page message if this page message is not for you. Okay? So this is basically what you need to do in an idle state. Now we talk about handover arrangement. So in particular for CDMA, is famous for doing soft handover. But handover or power control is only effective when you are in dedicated channels, traffic channel. When you are set up with dedicated traffic channel, then you have to worry about handover. You have to worry about power control. In other words, when you are in idle state, there is no dedicated channel set up for you. That's why you don't need to pay for anything. Okay? So if you move around, if you leave the current base station, by all means, you don't need any handshaking procedure. If you leave the current base station, enter into the new base station, you just go through this initialization state one more time. Okay? And you keep on listening and updating yourself with these overhead messages. Okay? Any questions? Now, so you can stay in the idle state forever. But there are 3 events. Let me erase this. So you can be in idle state for a very long time if nothing happens. But there are 3 events. These are event trigger. There are 3 things that will bring you out of the idle state. The first thing is called origination. That is, you press the send button. You call somebody else. You dial the digit 1, 2, 3, 4, 5, 6, 7, 8. Press the send button. That's the first thing that will trigger you to leave the idle state and enter into the next state. The second event is incoming call. This is called page response. You monitor the paging channel and you find that there is a page message dedicated for you. Then you need to leave the idle state and take action. The action is called page response. Okay? This is in response to this incoming call request. The third possibility is even you have no call request, or even if you have no paging message for you and you do not press the send button, there is a third outcome, a third event that will trigger you to leave the idle state. This is called location update. Remember, the network has to keep track of where you are. Okay? So how would the network be able to keep track of where you are? You need to report your location, either periodically or event trigger. Okay? So when some condition is satisfied, you need to leave the idle state and enter into the SS state to deliver a location update request. Okay? So this is something of the topic in the next chapter, so we'll talk about this later. So when one of these 3 things happen, you will leave the idle state and enter into something called SS state. Okay. So I guess this is a good time to have a 15 minutes break, and then we'll come back and talk about what exactly you need to do in the SS state. In the SS state, what you need to do is to tell the base station what you want. Okay. But then what exactly is the procedure? We'll leave it to after the break. So let's have a 15 minutes break.
先搞跳伞，跳伞那个挺漂亮的。 哦，好神秘！这个时候的日文可以记住。哦，对，百度后面都是这个。
我偶尔的糖蘸那种超好吃，就是不爱吃。这不是说我前单是什么意思？还有没有看过？我也觉得很早上，那个但是他不是那么他就是上面是发那个熏火的，那我可以什么的，这个没有，这个来，我可能超级还是很多人他们当时是那个中学的时候，我 get 不到他的出现。我感觉这个太长了，是把东西是一起相当于长的。是我们今天真是。这还是上了一个最初。一点伤，我觉得他对这个视频是有意思的。 这是不是？这公报。我说操，人生的老婆出现很大人。
Testing. Okay, let's resume. Now let's look at what happened. So I will explain how we do it first, and then explain why it's designed in this way in the access procedure. Okay. Now remember, when you're in idle state, the only way for you to talk to the base station is to use the so-called access channel. And access channel is the only available uplink common channel. Okay. So what you would need to do is according to this access procedure, is you will try to, now let's say you press the send button. So that trigger an origination request, and then you leave the idle state, enter into access state, right? So suppose you want to make an outgoing call request. So what would you need to tell the base station? Now you stand in the shoes of a protocol designer, let's say, right now. So after you press the send button, what do you need to deliver to the base station? What the base station needs to know in order to set up your call. For example, do you need to tell the base station what number you want to call? Of course, right? Otherwise, how would the base station know what to do with this, right? So you dial the number 123456798, and then you press the send button. So you need to tell the base station the coded number, right? What else? Besides the coded number, what else do you need to tell the base station? Do you need to identify who you are? Of course, right? Otherwise, how would the base station know whether you are my subscriber, right? So you also need to know, inform the base station who you are. So the way you identify who you are, there are for example, in 2G, in GSM, every one of you have a SIM card, right? There's a SIM card ID called IMSI, International Mobile Subscriber ID. So this is a unique SIM card ID. So no two SIM card in the entire network will have the same number, okay? So IMSI is actually your ID. But for some security consideration, so the protocol will minimize the chance for you to identify yourself using the IMSI. Because if somebody sniffs your transmission in the air, they know your IMSI, they can duplicate your SIM card, and that will not be secure enough. So usually instead of transmitting something called IMSI, you will transmit something called TMSI, Temporary Mobile Subscriber ID. So again, in the next topic, when we talk about core network, we'll talk about the mapping between IMSI and TMSI for security consideration. But let's not worry about this at now. So you will identify yourself by also telling the base station your ID, okay, some kind of ID. Okay, so at least you need to tell the base station these two information, right? So indeed, so the procedure in the protocol, they define a message called call origination request. So this call origination request is a signaling message, okay? So after the user presses the send button, the mobile has to find some way to deliver this call origination request message to the base station, so that base station will know what you want, okay? So, but the question is, how do you deliver it? So the access procedure is the following. So you first send a call origination request with a certain power called initial power. IP stands for initial power at a certain time, okay? Now, after you send it, you expect if the base station receives it successfully, you will expect an acknowledgement from the base station, okay? But you cannot wait forever. So what you do is you set a timer acknowledgement. So you start an acknowledgement timer. You start the stopwatch. If the timer expires and then you still do not receive an ad from the base station, you assume the transmission was not successful. Then what you do is You wait for another random time. After the random timer expires, you retransmit, but this time with a higher power. The power you retransmit is the previous power increased by power step. So power step is another parameter. So this IP power step, these are the examples of so-called access parameter message. So before you engage in access state, you should have already updated yourself when you are in idle state with this access parameter message. You should already know these parameters. Okay. So that's the second transmission. If you are so unlucky that after the second transmission, again, acknowledgement timer timeout, you still do not hear an ACK, then you wait for another random time and retransmit again with another increase in power step. Okay, so on so forth. You keep on increasing the power in your subsequent retransmission. And let's say after this num step attempts, you still do not hear an ACK. Okay, num step is another parameter. Then you start another random time and start all over again. Okay? If none of these attempts is successful at the end, after this mass response sequence attempts, then you give up. And then if you give up, that means something is wrong. Then you go back to the initialization state and start all over again. Okay? So that's the entire access procedure. So any questions? Should be pretty straightforward, right? Okay. Now the next I want to explain why the access procedure has to be arranged like this. Now in order to understand why, we need to first understand why the base station will not give you an ACK. Now imagine in this classroom analogy, I'm the base station, you guys are the mobile station, blindfolded yourself. Okay, you want potentially at random time you want to ask for my service. And you need to tell me what you want, right, by sending me a request message, okay? And all of us share this access channel. So if you say something to me, you send a request message to me, why I won't give you an ACK? What are the possible reasons? Why I won't give you an ACK? What are the possible reasons? Now imagine someone at the back send me the request message. What are the potential reasons? Let me be more explicit. Let's say somebody at the back whisper a request message to me. And why would I not send you an ACK? Very simple. I can't hear you, right? Your transmission power is too low. Because don't forget, you're blindfolded yourself. You don't know whether you're close to me or far away from me, right? So you just whisper with a soft voice. This is like you transmit your request with an initial power, which is pretty small. Right? So this power may not be sufficient to reach the receiver. Right? I may not be able to to receive the request message successfully. And therefore, I cannot give you an ACK, right, if I cannot receive it. Is that okay? So in response to this problem, so what is the solution? So that's why in the next transmission, I gradually increase my power, right? So the reason in my next retransmission, I don't retransmit with the same power. I retransmit with a slightly higher power. This is to overcome this potential issue of insufficient transmission power. Is that okay? So this is like somebody at the back, initially, you whisper your request to me. I can't hear it. I cannot give you an ACK. So next time after you timeout, acknowledgement timeout, you start to retransmit your request, but with a louder voice, right? Then keep on increasing your voice. Okay? So that explains this power ramp up. All right? Now, besides insufficient power, what are the other reasons that I may not give you an ACK? Now, if the only reason is due to insufficient power, then at the end of the sequence, you are literally shouting, right? You are shouting your request to me. Your transmission power should be, you're transmitting at maximum power. Then you should have sufficient power to reach me, right? But I still do not give you an ACK. So that means there may be another reason that I cannot give you an ACK. What are the other potential reasons? Let's say you have sufficient power to reach me, and still I will have potential problems of receiving your packet. Why? Again, think in the context of this classroom analogy. What would be the other scenario I may not be able to give you an ACK? If let's say everyone is shouting at your maximum power, still I may not give you an ACK. Why? What happens if there is more than one guy transmitting the request? If you transmit a request at the same time the other one transmit the request simultaneously, this is called interference, right? You have collision. The two requests will collide with each other. If you collide with each other, I won't be able to receive anything, right? Because it's a collided transmission. So collision is the second reason I may not be able to give you an ACK, right? Despite you have sufficient power. So in response to the second potential reason, what should I do? You notice that in every retransmission, after I time out with the acknowledgement, I don't immediately retransmit, right? Why not? After my timer acknowledgement, at this point of time, when the time acknowledgement timer expires, I know I have to give up, right? I know the base station will not give me an ACK. So why don't I retransmit immediately? Why I have to wait for another random time? You understand what I mean? So you have two timers involved before your retransmission. Why you need to wait for an additional random time before retransmitting? Now the question I'm asking is in the context of if you are the one to design the protocol. Let's say some days you work for vendors and you have the pressure to attend standardization meetings. So in the standardization process, not everyone is working on a physical layer. Some may work on protocol layers, right? So if you are the protocol engineers, you need to have the awareness what needs to be there in the protocols and why you need to have that kind of arrangement, right? That's the reason you need to know. In addition to how things work, you also need to have the awareness why things are designed in a certain way in order to have a holistic understanding. So why wait for the random time? What's wrong if I don't have the random time? What's wrong if after my timer acknowledgement expire, I just retransmit immediately? Now, if the reason I cannot hear an ACK is due to collision, that means in my first transmission, there will be another guy transmitting at the same time as me, right? Now, if after timer acknowledgement, I immediately retransmit, then that second competitor will also transmit at the same time, right? So if I don't have the second random time, then this kind of retransmission will not be able to resolve the collision issue. Because if there is a competitor at the first attempt, it will be guaranteed to have the competitor will be transmitting at the same time in a synchronized manner in the second attempt, third attempt, fourth attempt. Is that okay? So the random time is to spread out the chance. So if I'm that unlucky that in the first attempt there is a competitor colliding with me, since we have a different random time realization, right? So I may not be that unlucky that in the second attempt the competitor will collide with me as well, right? If I'm that unlucky, the second attempt is also colliding. Then I may not be that unlucky. In the third attempt, we end up having the same random time realization and end up colliding with each other in the third attempt, right? So you see that the chance for us to collide in the subsequent attempt is decreasing exponentially. Is that okay? So that's why we need to wait for the random time, because every competitor may have a different realization of the random time. So therefore, if we collide in one attempt, we may not collide in the subsequent attempt. But if without the random time, then the retransmission timing is deterministic. It's the same for everybody. So if I collide in the first attempt, I will guarantee to collide in the second attempt and third attempt. Is that okay? So that's why the random time arrangement is to account for the second potential reason of collision. Now, I won't know which case I will hit, right? In general, you do not hear the ACK from the base station. It could be due to insufficient power. It could be due to collision. You never know. Okay, so that's why in the protocol, you try to address these two potential reasons. So on one hand, in between retransmission, you increase the power, you warm up the power in response to the first potential reason of insufficient power. And in addition, you retransmit with a random time, so that's in response to the second potential reason of collision. Okay? So in this way, hopefully one of these attempts will get through, either with sufficient power or with sufficient attempts that you don't have colliding partners, you don't have colliding competitors in one of these future attempts. Is that okay? So random time is critical to average out potential collision. Now, you may wonder, why do I need to, collision is something I can understand, but what about the power? Now, if there is a potential reason that my transmission power is not sufficient, then why not everybody just start with the maximum power? So, doesn't matter you are close to me or far away from me. What's wrong with you just in your initial attempt, you are just shouting at me. So in this way, you will make sure you won't have insufficient power, right? So why not we do this? What's wrong with everybody shouting at me in sending the origination request? This will save the trouble of ramping up the power gradually, right? Why not? Well, imagine in this classroom, right, if we practice this transmitting the random access in maximum power. So you will hear, on average, everyone sampling, if there's some observer observing the classroom behavior, that guy will hear the classroom being very noisy, right? Because everybody is shouting, right? And remember, this is uplink. Uplink is operating using random CDMA. And remember, what's the capacity limit for random CDMA? How many users you can support depends on the interference margin between your interference floor and the maximum tolerable interference, right? This gap. If everybody is shouting on the random access channel, that means the background interference will be very high, right? If the background interference is very high, there is only little room for you to accommodate additional users. So in other words, it will jeopardize the capacity of the random CDMA in the uplink. So therefore, to maintain a reasonable capacity in the random CDMA uplink system, you observe across all the protocols, they try to minimize unnecessary transmission. So you start with a humble voice first, instead of shouting at the beginning, hoping that everybody will just transmit with just the sufficient power, okay, without excessive power. Because this excessive power, excessive transmission is not free. This excessive transmission will raise your interference level and reduce the capacity. Is that okay? So for every random CDMA system, you always have this behavior. Now, this is not free. There is a trade-off for this arrangement. The trade-off for this arrangement is you may have to try several attempts before you warm up to the sufficient power level to send your request. So that translates into access latency. Okay, so instead of transmitting once, you may need to transmit a few times. So, and that will be basically a delay of a few hundred milliseconds. But a few hundred milliseconds is fine in the context of call setup, right? Because when you press the send button, you won't mind waiting for a few seconds, right, for the call to set up. So this is a good trade-off, right? You rather trade off the access delay with this minimizing the unnecessary transmission on the uplink. Okay, so that's the reason for random access. Any questions? Okay, if not, so after you successfully, let's say you keep on doing this access procedure and one of these access attempts successfully get through the base station, then you will leave the access state and enter into the final conversation state. Okay, so in the final conversation state, there will be some subsequent handshaking between the mobile and the base station. So these are the snapshots. So for example, this is the origination request message sent through this access channel from mobile to the base station. Let's say in one of these access attempts, base station successfully receive it. After base station receive this call request message, the base station has to set up the traffic channel, set up the downlink traffic channel, okay? Allocate one available downlink traffic channel and try to send null data to the mobile, okay, on the traffic channel. At the same time, it will send a channel assignment message. Because this traffic channel, let's say, is delivered using a certain watch channel. Let's say it's W60, okay? So let's say the base station look through the available downlink channel and decide to spread the traffic channel using W60, okay? But the mobile station as a receiver doesn't know the right code, right? Remember, successful despreading requires knowledge of the right code and the right time. The mobile at this point just know the correct despreading timing because mobile has despread successfully the pilot channel, right? So it knows the right despreading timing. But mobile doesn't know the despreading code for the traffic channel, okay? So base station will inform using explicit signaling the channel assignment message to the mobile station. So this is the acknowledgement that we are talking about. This is a channel assignment message sent from base station to the mobile station. This channel assignment message will contain W60 as the spreading code for the downlink traffic channel. So mobile station receiving this channel assignment message will know W60 is the desthreading code for the downlink traffic channel for him. Okay, so mobile station will then start desthreading the traffic channel. So it has to confirm it can receive 2 consecutive good frames. And then with these 2 consecutive good frames received, the mobile station start transmitting on the uplink traffic channel. And then in return, the base station has to confirm it can receive 2 consecutive good frames in the uplink traffic channel. Okay, and then base station will send back an acknowledgement. Okay, acknowledge good uplink reception, and then further handshaking, and then the speech frame exchange, and then the 2 sides will engage in conversation. So that will be the handshaking involved. Is that okay? Now, question. Let's say you're in a mobile station. After you receive the channel assignment message, you know W60 is the desthreading sequence for the traffic channel. How do you know the frames you receive are good? The traffic frame from the downlink traffic channel sent to you contains 101010, right? Random data. How do you know the traffic frame you decode is good or bad? How do you know whether the traffic frame is good or bad? You don't know the data ahead of time. Now, so there is a technique. Every traffic frame has CRC, cyclic redundancy check. Okay? So this is like a checksum. By computing this checksum locally at the receiver, you know that if the checksum is 0, then you know that the data you receive, with very high probability, the data you receive is correct. Okay? Without knowing what are the data you should expect. So this is a checksum arrangement. So all the traffic channel, downlink or uplink, has this CLC checksum protection for error detection. This is called error detection. Okay? So again, in this arrangement, you will see that also the mobile station will not start transmitting on the uplink traffic channel until it confirms the downlink traffic channel are good. Okay? This is again to avoid unnecessary uplink transmission, so as to try to keep the interference level as low as possible on the uplink. Okay? Now, so this is basically the entire handshaking of the so-called call origination request. Okay? If you press the send button after this many handshaking, at the end, you will have a traffic channel set up for you, and you start to pay for the airtime. Okay? If you call your friend for 2 minutes, you just pay for 2 minutes of airtime. All right? Now, what about, erase that picture. What about incoming call requests? Now, for incoming call request, this is the second event that will trigger you to leave the idle state and enter into the SS state, right? The whole procedure is very similar. The only difference is when you press the send button, what you try to send in the SS attempt is the call origination request. But if this is due to an incoming call, a page response, what you try to send in the SS attempt is called page response message. Okay? So here, you go through similar handshaking, except that here, the mobile deliver a page response message to the base station in response to this incoming call request. And then base station will set up the downlink traffic channel, and then mobile station, after confirming the downlink traffic channels are good, will send the uplink traffic channel, and then negotiate the surface option, and then finally exchange a speech frame, start the conversation. Now, in this second scenario, incoming call request, when will the mobile phone ring and alert the user? Because now your mobile is, you don't know there is somebody calling you, right? So again, standing in the shoes of a protocol designer, somewhere the base station should inform the mobile station to ring, right? To ring the ringer, so that the user will be, your mobile phone will ring. You know there is somebody calling you, right? At what stage should the mobile station ring? I'll give you 2 choices. The first choice is as soon as the mobile station receives a page message. That's option A. That's A. B is somewhere here after mobile station and base station confirm the traffic channel in both sides. When should the mobile station start to ring? Of course, the second case, right? Because if you ask the mobile station to ring at the initial stage when mobile receives the page message, Then user pick up the call, but this is still in the middle of the handshaking. So it could happen that the traffic channel is not successfully set up. It could happen that there is no available traffic channel. Many things can happen in the handshaking procedure. So you only alert the user when everything, the traffic channel in both directions are properly set up. Only at that stage, your mobile phone will, then in this case, the base station will send an alert message. The mobile station, based on the alert message, will ring, and then the user will be aware that there is an incoming call. You pick up the call. Is that okay? So that's why if you have experience using, well, some of you may have this experience. Let's say you are sitting quietly in a library with your laptop and your mobile phone on the side, right? So nothing happens, and then suddenly you start to see the screen flicker. Seems like there is some interference. And after a few seconds, your mobile phone will ring. Have you experienced this kind of effect? You know what I mean? You can try. You can put your mobile phone next to your laptop, and then ask your friend to call your mobile phone. Before the mobile phone ring, you will start to observe the laptop screen will flicker, will have some kind of a disturbance. And then a few seconds after this disturbance, the mobile phone will start to ring. The reason is because when the mobile phone rings, it's already in the later part of this handshaking. So the reason that the screen will flicker is because before the mobile phone actually rings, the mobile phone receives a page message. When the mobile phone receives a page message, it will leave the idle state and enter into the active state. So it will start to transmit this page response message with warm-up power. So this transmission will generate, because it's transmission from the mobile station, it will generate EM interference. And this EM, electromagnetic compatibility issue, will interfere your screen. Okay, so when your screen flicker, this is during this warm-up procedure, when the mobile station is transmitting quite large the power, and that will cause interference to your screen. But still, you don't hear anything because this is just the beginning. When mobile stations try to send a page response message to the base station. And why after a few seconds? Because after a few seconds, when both the downlink and traffic channel are properly set up, then base station will send an alert message to the mobile station, and only then the mobile station will ring and user pick up the call. So that's why the screen flickering happens before the phone ring. It's always correlated this way for this reason. Is that okay? Now, one final question we want to discuss is about the same question. Okay, so in designing the call origination message, right, we know we need to have a coded number. We also need to identify who you are, right, so that the base station, the infrastructure will know what to do with your call request. So the third question, the other thing is, do we need to indicate the type of call? That is voice or data call in the call request message. Now, in 2G system, it's a digital cellular system. The radio interface is designed to support transmission of digital payload. Okay, so because of that, there are two potential. Let me draw the picture for easier explanation. Now, if this is the base station, this is the mobile station, and this is the radio interface. In IS-95, this is a digital cellular system. Digital cellular system means once every 20 milliseconds, there is a traffic frame delivered between the mobile and the base station. Okay, you can think of this traffic frame as a bus. So every traffic frame can carry some digital passengers. We call this digital payload. Let's say a number of bits, let's say 300 bits. Okay. Now, as the digital cellular interface, the radio interface is a digital cellular. So that means it will be able to deliver every frame, every bus will be able to deliver, let's say, 300 bits, 300 passengers. Okay, and that's what the radio interface guarantee. You will be able to deliver 300 bits from mobile to the base station every 20 milliseconds, and vice versa, let's say. Okay. Now, this digital payload can come from two sources. It can come from the mobile station. It can come from compressed speech. That's for voice call. So if you make a voice call, this 300 bits will be coming from the output of your compressed speech encoder, okay, just like MP3. That's one source of digital payload. A second source of digital payload would be from data. For example, if you have a laptop, through the laptop you want to send a file through the mobile to the other side, then this 300 bits may be coming from a file. Okay, so these are the two sources of the digital payload. But no matter what are the source of these 300 bits, the radio interface just guarantees it will deliver 300 bits every frame. Okay, so that's the digital radio interface. So that's the background. Now, back to the picture. You are now a protocol designer. In the call origination request, do you need to indicate the type of call? That is the source of this 300 bits. Do you need to indicate in the call request message that this source of the digital bits are from voice or from data? So this is a 1-bit information. Do you need to have this 1-bit indication in the call request message? Understand my question? Do you need to indicate the type of call? Where are these 300 digital payload coming from? Is it coming from voice or is it coming from a file? Do the infrastructure need to know? Now you may be tempted to say, why do I care where these 300 bits are coming from? The radio interface just guaranteed to deliver these 300 passengers from mobile station to the base station. When the frame reaches the base station, these 300 passengers get off the bus and move on, right? So why do I need, if you're at the base station, why do you need to know? The fact is, base station really doesn't need to know. But you still need to indicate the type of call in the request message. This is because the base station is not the destination for this call request message. The infrastructure is more than just the base station, as I showed you initially here. The infrastructure has base station controller, also mobile switching center. Okay? So if you look at the end-to-end picture, the infrastructure as a whole needs to know the type of call, because with different types of call, if you're making a voice call, the infrastructure needs to terminate your call with a speech decoder. If you're making a data call, the infrastructure needs to terminate your call with some other entity. Now, what is the meaning of this? Now, if you look at the voice call, so the source of this 300 bits is coming from a speech encoder, which is doing the speech compression, right? So the input is your voice. Your voice goes through the speech encoder, trying to compress it. So this is compressed speech. This compressed speech will enter the bus and go through this digital radio interface. And at the base station, it will leave the bus. But the base station is not the final destination. If this is a voice call, the destination would be to the PSTN, right? So if, let's say you make a fixed line call. If the destination is the PSTN, remember in day one, I talked about the interface. The data path to PSTN is dot wave format, right? It's a PCM 64 kilobit per second format. It's called, think about that as dot wave. But the encoder speech, the 300 digital passenger getting off the bus is coming from a compressed speech, is a proprietary format. So if you just move this, let these 300 digital passengers enter into PSTN directly, the PSTN won't be able to decode the speech packet because the format is different. PSTN only expect all the incoming data packet are encoded using dot wave format. But this 300 passengers is coming from a compressed speech. Where is it here? Yeah, it's coming from a compressed speech. Okay, so this is like you pass an MP3 file to a dot wave decoder. The dot wave will not be able to decode anything, decode your original voice, right? Because the format is not compatible. So therefore, in order to complete the speech path, somewhere in the mobile switching center before moving to the PSTN, you need to terminate this call with a speech decoder. That is, if you think of this as an MP3, you need to have an MP3 decoder so that the output of the speech decoder becomes dot wave. Then you deliver the dot wave format to the PSTN. Is that okay? So that's why the infrastructure needs to know the type of call, because they have to prepare different entity to terminate your call. If this is a speech call, the infrastructure, not the base station, but the infrastructure, mobile switching center, precisely, needs to find a speech decoder to terminate your speech encoded packets so that the output becomes a standard dot wave file, dot wave format, so that it can be understood by the PSTN. Is that okay? Now, on the other hand, if you're making a data call, that means there is no speech encoder here. The 300 digital passengers are coming from a file. If that's the case, then it doesn't make sense for you to terminate this call with a speech decoder, because it's like feeding a data with an MP3 decoder, but the input is not MP3 format. Then the output of the MP3 decoder will be rubbish, right? So if you're making a data call, then you need to find something else to terminate your data call. Now, in order to understand the data call arrangement, so let me again explain the end-to-end picture. So in those days, this is in the 90s. So in the 90s, in the fixed line, how do you access the internet? It's not like today. Today, you just plug your computer to the Ethernet socket, and then you just get online all the time. But in those days, it's based on dial-up modem. So if you subscribe to an internet service provider, they will just give you a telephone number. Let's say the telephone number is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that will be the access number to the internet service provider. So if you are at home, let's say this is your laptop, you connect through the modem. The modem at that time is called V.90, which is the standard of the modem. Through the telephone socket RJ45, you connect to the PSTN. And then the PSTN, this number, will be connected to the ISP, where the ISP also terminate the telephone socket with the V.90 modem. Okay? So when you want to access the internet, you configure the modem to dial this number. When you dial this number, it will make a PSTN call. The PSTN receiving this destination number, it will set up a data path to the destination number of the ISP. So this is our ISP, Internet Service Provider. So after this layer 1 get connected through the PSTN, the two modem, V.90 modem in your laptop and the V.90 modem at the ISP, they will start to talk to each other. So that's why after you get connected at that time, after the ISP answer the telephone call, you will start to hear this blah, blah, this kind of noise, okay? And that is actually the handshaking between the two V.90 modem to negotiate the data rate, etc. for the layer 1 connection. After the layer 1 negotiation is done, then you don't hear any noise anymore, okay? And then at that time, that means the layer 1 is established. After you establish the layer 1, the next step is there is a point-to-point protocol, or PPP protocol, at the laptop. We'll negotiate with the PPP protocol at the ISP. So this is for authentication. They will check your username, password, and then they will assign a public IP address to your laptop. And after successful handshaking, then the IP layer of the laptop will be allocated a public IP address. So this will be the IP. Then the internet service provider will be connected to the internet. Okay, and since you now have the publicly available IP address, so other server in the internet can receive your IP packet. They can also send an IP packet to you with this IP address. And let's say you want to browse the internet. The next step is to have a TCP layer. So you set up a socket which is end-to-end between your laptop TCP and the server TCP. This TCP socket will be end-to-end transparent to all the routers in the internet, right? And after that, you have, based on the socket, you do HTTP. So that will be the end-to-end picture at that time for you to browse the internet. You need to use the modem to dial the number, right? And then this number will get you a layer 1 connection into the ISP. And then the V.90 modem on both sides will handshaking. After finishing handshaking, you have a layer 1 connection established. And based on this layer 1 connection, the next layer protocol step will handshake with each other one by one. Okay? Now, so this is at home, right? Now, the ISP doesn't care whether you are at home or outside. So if you are outside at that time in a 2G network, they also provide you an option that you can connect to the internet, the dial-up ISP, when you are outside using IS95. So if you are outside, what happened would be let me use a different color. So then this will be the IS95 network, okay, the CDMA network. And then that will be the base station controller, okay, etc. And then this is your mobile handset, okay? But then your laptop, you bring the same laptop outside, right? At that time, this is your laptop. So how do you access internet outside? When you access internet, at that time, the mobile station have on the side of the mobile station, they have something called infrared port. Now, of course, nobody is using infrared anymore. You just think of infrared as now the modern days Bluetooth, okay? So through this infrared, you connect, it's a COM connection. You connect to a serial port of the laptop. So in other words, the laptop will see your mobile as a COM device, okay? Let's say it's connected through Bluetooth to your COM1. So when you want to access internet outside, what you need to do is you have to, through the COM1, ask this mobile to dial the number 1, 2, 3, 4, 5, 6, 7, 8, right? So you need this mobile to make an outgoing call request. So this mobile will send an origination request through the access attempt we just explained to the base station. Base station will move on to set up the entire call path, right? So since 1, 2, 3, 4, 5, 6, 7, 8 is a fixed line number, so the IS95 base station and base station controller and the mobile switching center eventually will set up the voice path, will set up the path to the PSTN because it's a fixed line number. PSTN will then continue to set up the path to the ISP because this is the destination number, which is at the PSTN, right? So now ISP answer the call. The ISP will hear an incoming call request, right? ISP answer the call. The modem of the ISP answer the call. Now, here is the problem. When it answers the call, the ISP doesn't need to be aware you are outside or inside. The V.90 modem of the ISP, after answering the call, it will start to do handshaking with the V.90 peer, right? But if you look at the upstream here, in the entire path, there is no V.90, right? Well, you can say there is a V.90 modem in the laptop, but don't forget, you have bypassed this. This V.90 may be your COM2 device, but you are using COM1 device to set up the call. So on the COM1 device, there is nobody speaks V.90. Understand my problem? So if you just do it this way, after the ISP answers the call, the V.90 will try to do handshaking, but there is no response, and then the call will be dropped. So you won't be able to connect to the internet this way. Is that okay? Because there is no V.90 to do handshaking with the ISP. So in order to support, for the IS95 to 2G mobile network, in order to support this kind of data demand, so they cannot just terminate your call this way. So they have to terminate your call by, let's use this picture. Instead of routing your call to the mobile switching center, they route your call to a special guy called interworking function, IWF. This interworking function is a physical layer gateway. So if I draw this here, so there will be an interworking function here. The interworking function is a physical layer gateway. A gateway is like a protocol translator, okay? So this interworking function will be able to speak V.90 on one side, and then IS95 proprietary data format on the other side. So this IS95 format will terminate into the IS95 format in the IWF. And then here you will do the translation from the IS95 proprietary data format into the standard V.90 format, okay? So in this way, you set up a call to this ISP answer the call. And then V.90 modem and the ISP will try to do handshaking with the upstream v.90. So in this way, the v.90 handshaking will be between the IWF and the ISP. Is that okay? So these two guys will do handshaking. After the handshaking is done, then the layer 1 connection is no longer end-to-end. The layer 1 connection between the laptop and the ISP consists of 2 segments. This is IS95 proprietary, and then this is v.90. Is that okay? So there is 2 segments in the layer 1. Then after the layer 1 is established, the remaining handshaking is the same as if you were doing this at home. The next level is PPP. Through this 2-segment layer 1, this PPP protocol will handshake with PPP protocol at the ISP. So this guy will ask you for username, password, and then distribute the public IP address to your laptop. And then based on this activated IP layer, you have a TCP. You set up a socket between the laptop and the web server. And then through the socket, you'll have HTTP application running on top of that. The rest will be the same. Is that okay? The only difference is the establishment of a layer 1 connection. You cannot just route the call to the PSTN without this interworking function, because if you do that, there won't be any v.90 peers to handshake with the v.90 in the ISP. So now, because of that, if you're making a data call for this kind of scenario, the infrastructure needs to know so that it will route your call to an interworking function instead of the mobile switching center, and terminate your call with this interworking function gateway instead of a speech decoder. So now you see that if in this scenario you terminate this data call with a speech decoder, then this is ridiculous, because the input to the speech decoder is not the compressed speech format. And if you input some arbitrary stuff into the speech decoder, the output will be rubbish. Okay? And then in this case, you won't be able to connect to the interworking function. You won't be able to connect to the internet service provider. Is that okay? So because of that, although the base station indeed does not need to care where are these 300 bits of digital payload coming from voice or from data, base station doesn't need to know. But the infrastructure as a whole needs to know, because the infrastructure needs to prepare different parties to terminate your call. Depending, if you make a voice call, the infrastructure, namely the mobile switching center, needs to terminate your call with a speech decoder. If you're making a data call, the interworking function needs to terminate your call. Is that okay? So because of that, even though the radio interface is transparent, like digital passengers, but you still need to indicate, erase that, the type of call, the 1 bit extra information in the call request message. Is that okay? So that's also another example. As a protocol designer, you need to have this awareness. What is needed, what is not needed. And when you develop this awareness, you need to have the idea that it's never just between 2 points. So the mobile network is more complicated than what you think. It's not just at the base stations. Some of the protocol will terminate at the base station controller. Some may even terminate into the mobile switching center. So depending on different terminating peers, you will have different consideration. Okay? So you need to have a holistic picture when you design the protocols. Okay? So that is the call processing. So with this, hopefully you understand the mechanism behind the scene. After you press the send button, there are a lot of handshaking behind the scene. And that is after this that you will. Now, in both cases, in IS95, the mode of connection is what we call circuit switch. So even if you make a voice call, you're charged by the air time, the so-called how many minutes you engage in the call. If you make a data call, at that time you're also charged by air time. Okay? Because even in the fixed line dial-up modem, you are also charged by minutes, by the time that you maintain connection. So that was the mode of internet connection at that time in the 90s. Now, of course, you don't charge by airtime, you charge by data volume, right? You can be online 24 hours without paying for anything, as long as you do not transmit packet. That is the new way of connection. It's called packet switch connection. So which we will talk about this for 3G, okay? Now, obviously, I don't have time to talk about power control. So next time we'll finish up with the power control and handover, okay? And then let me stop at this point.